Okay. Okay, fine. So in the last class, we were looking at some expressions for work done in an impulse steam turbine as well as the then we looked at the maximum work done. What is the expression? What will be the condition? All those things. Then we were deriving the expression for work done for a reaction turbine, and we stopped at the W is equal to maybe in terms of U V1 or in terms of phi. So now, so what will be the condition to obtain the maximum expression? Now, if you want to obtain the maximum condition, so we have to look for certain things. Now, look at this expression. So I have this expression, which is equation number 6. So W is equal to 2V cos alpha 1 minus U into U. Okay. Now, for any given value of alpha 1, see, from the expression 6, let me put it. See, from the equation 6, okay, for any given value of your, either it can be with respect to alpha 1 or beta 2, so whatever it means, for any given value of alpha 1 and speed n. So if I want to maximize this, what should be the condition? I should able to differentiate this u6 equation 6 with respect to u and equate it to 0. So that's what I'm trying to do here. So d by du of this expression, that is, I'll open the bracket, this will be 2v1 u cos alpha 1 minus u square, okay, is equal to 0. Now I'll try to differentiate this. If I differentiate, what I'm going to get actually, this will be 2v1 cos alpha 1, okay, minus 2u is equal to 0. So now if I simplify this, what I'm going to get actually, so this will be 2v1 cos alpha 1 is equal to 2u. So 2 just simply they cancel out. So your u will be v1 cos alpha 1. If I call this as equation number 8. See, for the maximum condition, your peripheral velocity or blade velocity u is equal to v1 cos alpha 1. If you look into the similar kind of expression what we add for an impulse machine, your u was equal to v1 cos alpha 1 by 2. So that's the difference. Okay. Now, what I will do, I will take this equation 8, that is u, and substitute in my 6. Okay. Substitute the value of u. Substitute the value of u. Okay. Substitute the value of u in equation 6. So then what will happen? That will be the maximum condition. That is, W max is equal to 2 times your V1. So U I will write it as V1 cos alpha 1. Okay. 2 V1 U cos alpha 1. Already I have, then one more cos alpha 1 minus, okay, I'm going to write it is V1 cos alpha 1 square. Okay, this is the expression what I have. So now this one I can write it as, this will be 2 V1 square cos square alpha 1 minus V1 square cos square alpha 1. So simply I'm going to get your W max is equal to, so 2 V1 cos square alpha 1 minus V1 square. So it will be only V1 square cos square alpha 1. So let me call this as equation number 9. So for the maximum condition, so the work done expression is W max is equal to V1 square cos square alpha 1. But your simple work done expression is W is equal to 2 times your V1 U cos alpha 1 minus U square. Or if I want to write in terms of, see, this is a special thing. What I wrote this one, no? This is a special thing where sometimes they may ask you to obtain the expressions for work done in terms of speed ratio. So in that case, just substitute for phi. The speed ratio is equal to ratio of your peripheral velocity divided by your maybe your v1, that is your absolute velocity. I may write in terms of phi. So these are the different ways of writing your work done expression for a reaction turbine. See, once you have written this kind of expressions, so for both impulse and reaction turbine, so the last topic what is left out as per your syllabus is the multi-stage axial flow machine, multi-staging. Okay, fine. Now, when we will go for multi-staging, as I told, when we go for compounding of your steam turbines. So, multi-stage axial steam turbine. So, I am not going to write any expressions and all, but I am going to just discuss. Okay, as per the syllabus, only discussion. Now, if you want to understand this actually, let me take a three-stage turbine. Let me take a three-stage turbine. So, a simple as an example, I am going to take a minimum I need to take a two-stage. Let me take a three-stage steam turbine, three-stage steam turbine, and let's try to write the velocity triangle. As I told, I am going with an axial flow machine, so my velocity will be same. That is, the blade velocity will be the same. So if I try to write it, actually, this is my velocity. Let me fix this u. That means your blades or your shaft will rotate at the same speed. Now let us try to write the first stage velocity triangle. Okay, this will be your straight line. Okay, this will be your, let me call this as V1. In that case, this will be alpha 1. If I try to close this particular triangle, inlet triangle, this will be my, okay, this will be my VR1. Okay, then if I try to complete my velocity triangle, so I need to write for your components of your V1. So one will be your VF1. So this will be my VF1. So this will be my VW1. Okay, so that this will be my beta 1. I got my inlet velocity triangle for the first stage. Look at this. This is your first stage, means I will be writing the velocity triangles only for the rotor, because in the stator the fluid will be just guiding, that's it. The velocity, there is a change of velocity, that's it. There can be a drop in the velocity, that's it, because of the friction or whatever it may be. Okay, now first stage velocity triangle or rotor. Now let me try the exit velocity triangle. So if you want to write the exit velocity triangle, so it will be something like this. This is my VR2. So this is my VR2, and this will be my V2. This is my beta 2, and if I complete with my components of your V, so this is my flow component, this is my whirl component. Okay, so if I try to close this, this will be VW2, and this will be VF2, and this will be my alpha 2. See, now your V1 is the absolute velocity with respect to the inlet at the rotor, and V2 is the velocity with which the fluid is going out. Now look at this. What is the velocity which is coming out of your rotor? It is V2. Now when I go to the second stage, if there is no friction, your V2 will be the velocity for the inlet to the second stage. Okay, now if I try to draw the velocity triangle actually for this particular case, so what will happen? I should able to draw the same thing. Okay, I should able to draw the velocity triangle. Look at this. This is it. Your blade velocity will be the same. Okay, this will be the blade velocity. It will be the same. It's a single thing. So now if I try to draw the velocity triangle for the second stage, so your blade velocity will be the same. That is, this will be once again your U component. Because in axial flow machine, steam turbines, I told your U1 is equal to U2 is equal to U3. So your U velocity will remain the same. Now what will be my V3? See, V2 will be the inlet to air. So what will happen? So that will become, see, whatever the component, this particular thing, what I am showing here, this component of velocity, V2 will be the velocity over here. So this will be my V2, literally speaking. So that will be my V2 with an angle, so alpha 2. Understand? See, if there is no friction, V2, this V2 will be the same. If there is a friction, this particular component, if I call this as V2 dash, your V2 dash will be slightly smaller than your V2 if there is a friction. So the friction factor may be 0.95 times or 98 times. So a smooth blade or a new blade will have a very less amount of friction. So the carryover velocity is much better. So ideally speaking, that's why we prefer a very smooth or clear blades. So that's one condition, requirement of your velocity or requirement of your blades. Now let us try to close this particular triangle. So I can close it. So this will be my, if I call it as VR2, I can close this particular thing. Okay, and close it. So this will be my VF2 and this will be my VW2. So this is my theta 2 and alpha 2. Now if I want to draw the maybe your V3, so VR3 will be something like this. It's a small triangle. This will be my VR3, okay, and this will be my V3. I can close with the components of velocity line. This will be my component. This is my VF3 and this will be my VW3. This will be my alpha 3, that is. This will be my alpha 3 and this will be my beta 3. So I got my second stage. This is for the second stage rotor. So this is the triangle, what I will be having. So what does it indicate? It indicates that the energy available at the first stage is more compared to energy available at the 2. That means in stages, the energy is getting absorbed. How we can do it actually? We can clearly visualize by looking at its velocities. As I told, in compounding and all, the kinetic energy gets absorbed or the pressure energy gets absorbed. So the kinetic energy and pressure energy both getting absorbed becomes a reaction turbine. If it is only kinetic energy is getting absorbed, it is an impulse machine or an impulse turbine. So looking at the velocity triangles, I can clearly visualize in multi-stage that the energy is getting absorbed as the steam flows from first stage to second stage, second to third stage, and subsequent stages. Now this is for second stage rotor. Now how to extend for the third stage? So what will happen? I can extend this particular line further, and this also I can extend it further. Okay, and then I can draw a triangle. So the third stage triangle. This is to U. This will remain U. Okay, this will remain U. That means your blade velocity will remain same because all the shaft will rotate at the same speed. Now this V3 is there, which is the exit velocity for the second stage, and it will be the inlet velocity for the third stage. So it will enter at same velocity. That means, so it will enter at this velocity, that is V3. I have it alpha 3, and it will close with VR3. Fine. I can close this with a, this will be a smaller triangle slightly. If you draw to the scale, we'll be getting it exactly, we'll be getting it to the scale, because the values keeps reducing as you move from first stage to second stage. This will be my VF3, this will be my VW3, okay, and then if I want to close it, this will be my VR4, and then this will be my V4. I can close it with the VF4, and this will be my VW4. This is for a 3-stage or a third stage rotor. So closely if you observe, first stage to second stage to third stage, the velocity triangle is slightly becoming smaller and smaller. And also I told actually, so if V2 will be is equal to your whatever this particular thing, V2 from first stage, see, V2 from first stage will be equal to V2C. Let me write that. So V2 from first stage will be equal to V2 from second stage. That means no friction. Okay, V2 from first stage, okay, is equal to some friction factor. Let me call that as K into your V2 from second stage with friction. So this becomes your friction factor. The same rule can be applied to third stage also. So V3 is equal to V3 from second stage is equal to V3 from the third stage, no friction. V3 from second stage is equal to some K2 or K1 into V3. So K1 into V3, where K1 is equal to friction in the second stage. So with friction, without friction. So with friction, what will happen? These velocities will slightly become smaller. That means your velocity triangle, that is energy available, will become smaller, so that I'll be able to get a smaller velocity triangles. So this is about your multi-stage steam turbine, axial stage or axial flow steam turbine. Now in multi-stage, you have to be very careful. One thing is, as I move from one stage to other stage, the energy gets absorbed, whether it can be kinetic energy or it can be your pressure energy, whatever it may be. This is about it. Okay, so if there are any doubts, so I'm ready for discussion before we move to solving some numericals. Any clarifications? Anything? You can unmute or you can raise your hand. We can have a discussion. So the theory part is done. We have to solve some numericals. See, I have uploaded the tutorial sheet in the Google Classroom. Just go through that. We'll try to solve 2-3 numericals. Today a few numericals and tomorrow a few numericals. Shall we proceed and solve the numericals? You should get some answer at your end.
Yes, sir.
Yeah, okay, fine. So we'll take up the numerical sheet. I'll show you the numerical sheet. It's available in the Dropbox. So it's there in the Dropbox for me. So I have around few 14 or 15 numericals I have put. Okay. So just check into that numericals. Tutorial 6, I think. Tutorial 6. I prepared a tutorial sheet. And just look into that. Okay. This is your tutorial sheet for the steam turbines. Okay, let me solve 1 or 2. We have some time. So let me start with one numerical, and if possible, we'll try to solve the 2 numericals. So I have some 14. So we'll see, can I add to these numbers? Okay, let's take the first numerical. First numerical, let me take it. A single stage impulse turbine has a diameter of 1.5 meter running at 3000 rpm. Okay. The nozzle angle is 20 degree. What is this nozzle angle? It is your alpha, flow angle. The speed ratio is 0.45. The ratio of relative velocity to the outlet to the value at the inlet is 0.9. Okay, that is your friction, that particular thing. Relative velocities, that is VR2 by VR1, whatever is that particular thing, it's taken as 0.9. The outlet angle of the blade is 3 degree less than the inlet angle. Okay, suppose if I take beta 2 is equal to some angle, okay, then beta 1 minus 3 degrees will be that beta 2. That's the meaning of it. If beta 1 is 45 degrees, your beta 2 will be 45 degrees minus 3 degrees. So that's the solution. So when you get the solution, you can easily get the other angle if you get one angle. Steam flow rate is 6 kg per second, the mass flow rate. Draw the velocity triangle or velocity diagrams and find the following. First one, velocity of the well, that is VW1 and VW2 both. Then axial thrust, that is axial force. Then the blade angles, both beta 1 and beta 2. And this being a power turbine, I need to look at the power developed. If it's a compressor or a pump, I look at the power consumed. Okay, here it is power developed. So let's try to write the data what is given. Then we'll try to go for solving the problem. Okay, solution. Let us write the what is the data given. That is given data. So diameter, this being an axial flow machine, it has a single diameter. So D is equal to 1.5 meters. So speed is equal to 3000 rpm. Then alpha 1 is equal to 20 degrees. Okay, then I have my speed ratio, that is phi is equal to 0.45. Then I have a friction factor. You can take it as K, which is equal to 0.9, and then I have my beta 2 is equal to beta 1 minus 3 degrees. Then I have my mass flow rate, which is equal to 6 kg per second. This is what the data given. What we are supposed to find? We are supposed to find the first thing, the whirl velocities VW1 and VW2. Then the second thing is your axial thrust. The third one is both my beta angles, beta 1 and beta 2. And the fourth one is the power developed. The fourth one is the power developed P. So these are the things which we are supposed to find actually. So before we proceed, let's first draw the velocity triangle. Okay, single stage. This is for the single stage. Let me draw it. So this is my as I told, I have the option of I am going from left to right for all the compressor and the pump, and right to left for turbine and all. So this is my sign convention, because depending upon how the work is done on the machine or work is done by the machine. Okay, this is my U. Then I'll be having the V1, which will be like this. So this is my V1. This is my alpha 1. Then I can have my VR1. Okay, then I can complete the triangle with other two components of velocity. So this is my VF1, this is my beta 1, this is my VW1. Okay, I got my inlet velocity triangle. So if I try to draw the exit velocity triangle on the same combined velocity triangle, so this will be my VR2, then I have my V2. See, what I am drawing is not to the scale. Some kind of methodology I am trying to use. If you want to, you can You can solve this problem using scale. I will show you in the tomorrow's class how to use your graph sheet to solve the numericals. Okay, to the scale. So let me show this. Okay. So this is my VF2, alpha 2, beta 2, and this is my VW2. So this is my velocity triangle. Fine. I will go with another thing that x is equal to, so this quantity, this is called as x, okay, and this I am calling it as y. So x is equal to VW1 minus u, and y is equal to VW2 plus u. Same what we have been using. And one particular thing you have to be very careful here. See, VW1 is in this direction and VW2 is in this direction. See what I have drawn. If suppose when you are calculating, suppose any one of the value changes or what you are going to get from your trigonometric relations, if these values are changing, you have to redraw your velocity triangle, because what I have drawn is not to the scale. So that can be eliminated, or if you want to draw to the scale and all, we can do it on a graph sheet. So tomorrow I will show you how to get the velocity or draw the velocity triangle on a graph sheet. Okay. Now, once I draw the velocity triangles, I need to calculate some of the things. Okay. The first and the foremost thing what I want to calculate is the blade speed. So the blade speed u is equal to pi d into n by 60. So what is the value of d? It is 1.5. Let me substitute that. Pi into 1.5 into 3000 divided by 60. So I am getting around 235.6 meters per second. So this is the value of your u. Now in the numerical they have given phi is equal to 0.45, which is the ratio of your blade velocity to your flow velocity. So what will happen to your V1? See, in that case, so your V1 is equal to your phi into u. I take the, sorry. It's actually, it should be V1 is equal to u by phi. It is actually u by phi, that is 235.6 divided by 0.45. I am getting around 523.8 meters per second. So V1 is equal to 523.8 and u is equal to 235.6. Now let us take the inlet velocity triangle. If you consider the inlet velocity triangle, what is cos alpha 1? Cos alpha 1 is equal to your adjacent, that is your VW1, divided by your hypotenuse, that is your V1. Okay. From the inlet velocity triangle, okay, from the inlet velocity triangle, cos alpha 1 is equal to your VW1 divided by your V1, okay, or I can write VW1 is equal to V1 cos alpha 1. Okay, what is the value of V1? Just now we calculated, the value is found to be 523.8. So I know the value of alpha 1. I can easily find the VW1. So VW1 is equal to 523.8 into cos 20. So from the calculator, I am getting this value as around 492 meters per second. I got the value of VW1. So now I can find the angle beta 1. What is tan beta 1 from the inlet velocity triangle? Tan beta 1 is equal to, okay, your VF1, that is opposite side, divided by your adjacent your x. What is your x actually? X is equal to VW1 minus u. Okay. Now from the same inlet velocity triangle, I can write tan beta 1 is equal to your Vf1 divided by x, okay, or I can, maybe I am calling it as x is equal to Vw1 minus u, that is 492 minus 235.6. So x is equal to 256 roughly, 256 roughly meters per second. So here if I substitute over here, beta 1 is equal to tan inverse of your Vf1 divided by x. Okay, let me substitute that. Beta 1 is equal to tan inverse of your Vf1 is how much actually? It is, so Vf1 will be, I can find that Vf1, I need to find the Vf1. So Vf1 I need to find. So Vf1 is equal to your V1 sin alpha. So I can need to find that. So sin alpha 1, I can write sin alpha 1 is equal to Vf1 divided by V1, or Vf1 is equal to V1 sin alpha 1, or I can write it is V1 is equal to 523.8 into sin 20. So Vf1 is equal to 179 meters per second. So let me substitute that. It is 179 divided by, okay, it is 256 roughly. 256. If I do that, if I take the tan inverse of that particular ratio, I am getting around 34.93 degrees, or roughly around 35 degrees. If you want to round it off, it is 35 degrees. 34.93 or 35 degrees. Now, this is your beta 1. How to find beta 2? In the problem statement, if you go and see, beta 2 is equal to beta 1 minus 3. So it is 35. If I take 35, round it off to 35, your beta 2 is 35 minus 3. Simple. So therefore, in the problem it is given as, therefore, beta 2 is equal to beta 1 minus 3 degrees, that is 35 minus 3. So this is your 32 degrees. Okay. And also they are given the friction factor, that is K is equal to VR2 by VR1, or I can call VR2 is equal to 0.9 times of VR1. So that's the meaning of it. That means your relative velocity at the exit is getting reduced. VR2 is equal to 0.9 times of VR1. But I don't know the value of VR1. So how to find the VR1? Just go here. Just go to your inlet velocity triangle. What is your sin beta 1? Your sin beta 1 or cos beta 1. If I sin beta 1, if I take Vf1 divided by VR1, or if I take cos beta 1, it is x divided by VR1. Any one of the things if I do, I'll be able to get my VR1. So from the inlet velocity triangle, I can write sin beta 1 is equal to Vf1 divided by VR1, or to the little bit of cross multiplication, VR1 is equal to Vf1 divided by sin beta 1. So just now we have found the sin beta and we have found the Vf1 also. Vf1 is 179 divided by sin beta 1 is 34.93. If you want to be more accurate, or you can find 35 also, doesn't matter. Maybe the values may change in the decimals. So VR1 is equal to 312 meters per second, roughly rounded up to 311 point some change you will get. You can round it up to 312 meters per second. So therefore, VR2 is equal to 0.9 into 3, that is VR1. So this is equal to 281 meters per second. So this is about your VR2 value. Now go back to this exit velocity triangle, because I need to find that particular VW2. If I want to find VW2, I will take this velocity triangle, that is cos, what is cos beta 2? Cos beta 2 is equal to y divided by VR2. So what is y? Y is equal to VW2 plus U2. So first I will find y. Then because I know the value of U, I can easily find VW2. Okay. So let me write that. From the exit velocity triangle, from the exit velocity triangle, I can write cos beta 2 is equal to y divided by VR2, or I need to get the y actually. So y is equal to VR2 into cos beta 2. So VR2 is 281, beta 2 is 32 degrees. Okay, let me find that. 281 into cos 32, I am getting 238.8 meters per second. This is the value of y. Now, but therefore, what is y actually? Y is equal to VW2 plus U. I need to get my VW. So VW2 will be equal to your y minus U. So that is 238.8 minus 235.6. So it is a very small value, 3.2 meters per second. So VW2 is equal to 3. So sometimes this value may come negative. If this value comes negative, this value, if it comes negative, then you have to change the direction in your velocity triangle. Then what is actually, so here from the velocity triangle, VW1 and VW2 both are in different directions. Suppose if VW2 is positive here, this will hold good. Suppose my VW2 comes negative, then velocity triangle is going to change. So then what is there to the right hand side will come inside. So VW1 and VW2 both will be in the same direction. Then most of your values are going to change. Your work done values are going to change. So VW1 minus of minus what we have taken, this will become only VAW1 minus VW2. So those are the things which will come. See, this will vary from different condition to condition or problem to problem. This will vary. So you have to be very careful when you are solving your numerical. Okay. So that can be avoided if you go by graphical method, which I am going to show you in the tomorrow's class. Now, for this actually, sin beta 2 is equal to VF2. Okay. So sin beta 2 is equal to, to add a page. So sin beta 2 is equal to VF2 divided by VR2. If you go here, look into velocity triangle, sin beta 2 is equal to VF2 divided by VR2, or VF2 is equal to VR2 into sin beta, I can find the corresponding VF2. Because I need that VF1 and VF2 to find the axial force. Okay, if you want to find the axial force, you need both that actually. Otherwise, it's difficult for me. So I need to find that VF2. For that actually, what I'm going to do, so I'm going to write from the exit velocity triangle only, sin beta 2 is equal to, okay, it is VF2 divided by VR2, or I can write VF2 is equal to VR2 into sin beta 2, or it is VR2, it is 281 into sin beta 2 is 32 degrees. I am getting around 148 meters per second. Okay. So once you have got this, what I need to find? See, we need to find the axial force. So to find that axial thrust or whatever it may be, F axial is equal to mass flow rate into difference in your flow velocities. That is VF1 and minus VF2. That is 6 into 179 minus 148. So this is around 181 newtons. Okay. Now to find the power. So this is the second thing. So beta angles are done. So the last one, power, I need to find. So what is your power? Mass flow rate into work done per or specific work done. Or what it is, this particular thing, it is mass flow rate into VW1 minus of minus VW, that is VW1 plus VW2 into U. Okay, let me substitute those values. So your mass flow rate is 6 into, so VW1 is 492. So your VW2 is actually, it is just small value 3.2 into 235.6 is my U. So your power value P is equal to, if I substitute roughly around 699 point something I'm getting, I can round it off to around 700 kilowatts. See, all the quantities, all the things which we are supposed to get from the numerical, everything we got it. So what we are supposed to find? We are supposed to find the